Hello everyone. I'd like to go over an example of a DFA which was drawn here by Michael Tichy, fall 2021, called Spooky Threes. So it's going to be a DFA that accepts binary strings that are divisible by 3. And this is a bit trickier than the DFAs that accept strings that are divisible by a power of 2. Because as I was showing in the notes, for formal description of DFAs, something that's divisible by a power of 2, all you have to do is look for a string of zeros in a row that it ends with. So, for example, if it's divisible by 8, that's 2 cubed. That means it needs to end in 3 zeros. But when I give you that's something that's not a power of 2, it gets a little bit more complicated. So the smallest example I can come up with that's not a power of 2 that's actually interesting is 3. So that's the one I'm going to look at. So first of all, I'm going to tell you the states that are helpful to look at are what the remainder of the number would be when divided by 3. So there's 3 possibilities when you're dividing by 3. One of them is a remainder of 0, the other one's a remainder of 1, and the other one is a remainder of 2. And when we start off reading a binary string, there's nothing, so we'll say it has a remainder of 0. Okay? Now here's what we got to think about. In these 3 different cases, what happens when we see an additional bit? What happens when we see an additional 1 or 0 as we're reading the string from left to right? So let's suppose that we're in the first case, which is divisible by 0. Or sorry, not divisible by 0. Nothing's divisible by 0. First case is that we have a remainder of 0 when dividing by 3. Okay? So that case is saying that our number n that we've seen so far is equal to just 3k for some k in the integers greater than 0. So I'll say z plus here. That would be the notation for a non-negative integer. Okay, so that's the case there. Now if we look at what happens when we, let's say, add a 1 to the end. Actually, let's start with adding a 0 to the end. So if we add a 0 to anything, we know that we're multiplying that by 2. That was the same kind of logic that we used to think about divisibility by a power of 2. Okay? So again, when we add a 0 to the end, that's multiplying by 2. So if n was equal to 3k, now n is going to be equal to 6k. And nothing has changed. Right? Still divisible by 3. Okay? Good. So I'm able to fill in the first arrow. I'll have 5 more to go. But so if I see a 0 and I'm already divisible by 3, I will continue to be divisible by 3. All right. Now if I add a 1 to the end, then what I can say is n is equal to, if n was 3k before, what I've done is it's like adding a 0 to the end, which multiplies it by 2, but then I'm going to plus 1. I'm going to turn that 0 into a 1. Okay? So now I look at this, and when I divide this by 3, this part of it is divisible by 3, but I'm going to have 1 left over, right? So now the remainder is 1. Okay, so again, hopefully that makes sense. Adding a 1 to the end, it's like adding a 0, right? Which is multiplying by 2. But I want to turn that 0 into a 1, so I have to add a 1. Okay? So that's the full breakdown there on what happens. Great, now I just knocked out another arrow, so that's saying, okay, if I am divisible by 3, but I now see a 1 as I'm reading this thing, I am going to be divisible by 1 with what I've seen so far. Okay. So hopefully you see what's going on. We're building up the string from left to right, starting from nothing, because that's how we would read the string, and then keeping track of how the divisibility changes. Okay, let's look at 1 now. So if we're, the second case is if we're at 1, then we have a remainder of 1 when dividing by 3. So in that case, we say n is equal to 3k plus 1, all right? For k a non-negative integer. So in this case, if we add a 0 to the end, well, we're multiplying by 2 again. That's what we're doing. So what I'm saying is, anytime I add 0, I multiply whatever it was by 2. So that's going to be 3k plus 1 quantity times 2, right? So the whole thing multiplied by 2, which is 6k plus 2. Okay, so now this is a little bit different. So if I add a 0 to the end of something that is 1, has a remainder of 1 when divided by 3, this is actually going to have a remainder of 2 when divided by 3, right? So I can see this part of it is going to factor out. The 3's go evenly into there, but we have a remainder of 2. Okay, so a 0 brings us from a remainder of 1 to having a remainder of 2 there. And then I can use similar logic to see if I add a 1 to the end. Well, again, it's like multiplying by 2, but now I'm going to add a 1. So interesting, I end up with 6k plus 3, which actually is divisible by 3. Okay, so this part is divisible by 3, and then what's left over here? 3, certainly divisible by 3. So if I'm divisible by 1, and I add a 1 on, I'm actually divisible by 3 again, so I can go back to the remainder of 0. Okay? Whoops, wrong one. I meant to go from remainder 1 to remainder 0. Okay, there we go. Good. Last one. Hopefully you're starting to get the rodeo here. So third case, remainder of 2 when divided by 3 is what we've seen so far. In that case, we would say that our number so far is equal to 3k plus 2. And so if we add a 0 to the end, well, we're going to multiply that entire quantity by 2, which is going to give us 6k plus 4. And looking at that, that actually has a remainder of 1 when divided by 3. So this part divides evenly by 3, and then so now I just need to consider what does 4 do. So 4 divided by 3 has a remainder of 1. Okay, so when I see a 0 and I had a remainder of 2, then I have a remainder of 1 after I add that 0. Right? So we go back here. And then finally, if I add a 1 to the end, then I'm just going to add a 1 to what I was just looking at. So that would be 6k plus 5, which is actually a remainder of 2. Right? So we just have the 5 here left after we take the 6k away, and that has a remainder of 2 when divisible by 3. So we're actually going to stay where we are if we see a 1. Okay, did I agree with Michael Ticci here? Let's see. So if I go back to our home page, let me scroll up here. I believe I did. The only difference is my DFA looks much more boring than his, because he's got some pumpkins and a spider. Okay, so I guess for him, I think it looks like the pumpkin represents the fact that we're starting. And actually I did forget one little thing here, which is the spider. If we are divisible by 3, then we have a remainder of 0. So this state is not only the start state, but actually the accept state as well. And that'll be true for any of divisibility that you kind of design this way, where you think of each state being the remainder that you would have. So if I was looking at divisibility by 5, for example, I'd have 5 states, 0, 1, 2, 3, 4. And same thing, 0 would be both an accept and a start state. All right? So hopefully that makes sense. And that is going to help you with some problems on the homework. because I'm actually going to ask you to do, I believe I asked you to do divisibility by 5 somewhere. Yes. Yep. So that's problem 1.3. And then I actually ask you to do a formal description to describe this in general. Right? So again, this is a general pattern. You can always look at this sort of thing. So here it was, 3k is what I started with if I was divisible, or 3k plus 2 if I had a remainder of 2. So in general, I'd be starting with, let's say we were trying to look at divisibility by q. So I would say qk plus r for divisibility by q with remainder r. And so you would just look at what happens to that when you see another 0 or another 1, and then describe that to me formally in the state transitions. All right? So let me know if you have any questions on that, and I hope that clears some of it up.